This is your presenter Asloob Mudassar, and I am presenting slide number 58 of the course on laser physics. Question is, define saturation. How will you calculate the total power per unit volume to be absorbed by the material to maintain a given population difference in the two levels of a two-level system, assuming a homogeneous line absorption? Also express this power in terms of the incident beam intensity and the saturation intensity. The answer is, when a material is exposed with a strong monochromatic electromagnetic wave of a frequency nu naught close to nu naught lying close to the resonant frequency nu naught of the two levels, the populations N1 and N2 of the levels 1 and 2 tend to equalize. A stage will reach when the power absorbed by the material will be equal to the power lost by the material. The material behaves as transparent and the phenomenon is referred to as saturation. Let's assume that at some time t, N1 is greater than N2, that is the population of the level 1 is greater than the population present in level 2. And let W is the transition rate of the stimulated process. That is, W is the transition rate of stimulated emission and also that of the stimulated absorption. That is, for both these stimulated processes, the transition rate is W. And 1 over tau is the transition rate due to spontaneous emission, including radiative and non-radiative transitions. Then the decay rate of the population of level 2 is given by, so dN2 over dt is equal to minus W, within parentheses we have N2 minus N1 minus N2 over tau. You see that we have this minus WN2. Actually this process is the stimulated emission process. And if you multiply W inside the parenthesis, you have a plus W into N1 due to plus sign, and N1 is the population of the ground state, and this then WN1 becomes the stimulated absorption. And then lastly we have a minus N2 over tau. 1 over tau is the transition rate for the spontaneous emission. So this is the third term, is the spontaneous emission term with the negative sign, because it will tend to decrease the population of level 2. So two processes will decrease the population of level 2. One is the stimulated emission process, which is minus WN2, and the second one is the spontaneous emission process, minus N2 over tau. And the population of N2 will increase due to the term which is plus WN1. So all the terms in equation number 58.1 are explained. Now introducing N1 plus N2 is equal to Nt, where Nt is the total power, is the total population. Delta N is equal to N1 minus N2. Introducing these in equation number 58.1, we can rewrite equation number 58.1 as given in equation number 58.2. That is d over dt of dn of delta n, which is n1 minus n2 is equal to minus delta n times, within parentheses we have 1 over tau plus 2w, and outside that one we have a plus nt over tau. So you see that if you substitute the value of nt over here, that is the nt is replaced by n1 plus n2, and you replace delta n with n1 minus n2, then you will see that you will get the same equation as in equation number 58.1. In steady state, d delta n over dt is equal to 0, which means that we want to keep, what is delta n? Delta n is equal to n1 minus n2, and we want to keep this difference constant with the time, because this is the requirement of our questions, to maintain a given population difference. So the population difference, for example, the given population difference is n1 minus n2, And if you want to keep this population difference, that is delta n is equal to n1 minus n2 to be constant with the time, then you see that its derivative will be equal to 0 and the steady state will be reached. So we have d delta n over dt is equal to 0. Setting that one, we are getting delta n is equal to nt over 1 plus 2w into tau as shown in equation number 3. To calculate the power absorbed per unit volume by the material. So let me recall that N1 is the population per unit volume, N2 is the population of level 2 per unit volume, NT is the total population per unit volume, and delta N is the difference in populations of volume 1 and volume 2 but per unit volume. So all these n's and delta n are per unit volume. To calculate the power absorbed per unit volume by the material from the incident beam, to maintain delta n, we multiply both sides of equation number 3 by W into h nu and designate it by dP over dV. So dP over dV is actually the power absorbed per unit volume. So for that one, we need to multiply both sides of equation number 3 by W into h nu, so that we can get the dimensions of dP over dV, that is the power absorbed per unit volume. So on the left hand side of this equation, we have delta n multiplied by W multiplied by h nu, and this is what has been designated as dP over dV. And on the right hand side, we have nt over 1 plus 2w into tau, and then we have multiplied in the numerator by W into h nu. So this is what we have obtained, the power absorbed per unit volume by the material from the incident beam to maintain delta n, that is the difference in population will be maintained if this much power is to be absorbed by the material, as shown in equation number 4. When the saturation condition is approaching, the stimulated absorption is compensated by stimulated emission, and the power absorbed by the material is released by the spontaneous emission process till delta n vanishes. Moreover, the stimulated process being faster have much shorter lifetimes, that is tau is much greater than 1 over W. You see that the spontaneous lifetime tau is much greater than in comparison with the time due to stimulated emission and stimulated absorption. That time is given by 1 over W, or this can be written as W tau is much greater than 1, and thus equation number 58.4 takes the form. So you see that using W tau is much greater than 1, the denominator becomes, in the denominator 2w into tau becomes much greater than 1. So we can ignore 1 over here, and we can write equation number 4 in the form that is dP over dV at S stand for saturation, that dP over dP at saturation is equal to nt over 2 tau into h nu, because the W will then cancel out with the W in the denominator will be cancelled out by the W in the numerator, and we are left with this quantity dP over dV. V stand for volume. dP over dV at saturation is equal to nt over 2 tau multiplied by h nu, and here tau is actually, you see that the lifetime of the spontaneous process, and 1 over tau is actually the transition rate due to spontaneous emission. So 1 over tau is the transition rate due to spontaneous emission, and tau is the lifetime of the spontaneous emission. So this is the power absorbed per unit volume by the material at saturation. You know that when we are talking about the saturation, then you see that the absorption rate is the same as the absorption due to stimulated. We can clearly say that stimulated absorption is balanced by the stimulated emission. And you see that in this equation, that is dP over dV at saturation, you don't see W over here. That is W, which is the transition rate due to stimulated emission or due to stimulated absorption, is not present. because the two processes compensate each other. That is, the stimulated absorption is being compensated by the stimulated emission. So that's why W is not present over here in equation number 5. And under that condition, the population of the two levels, that is the level 1 and the level 2, will be equal to NT by 2. That is, half of the total population will be present in level 1 and half of the total population will be present in level 2. So let me read the paragraph that this is the power absorbed by per unit volume by the material at saturation. At saturation, the population of each level will be N2 by 2. That is, half of the total population will be present in level 1 and also in level 2. Absorption coefficient sigma in terms of the photon flux capital F of the incident beam is defined as the absorption coefficient sigma is equal to W over capital F, where F is defined as I, which is the intensity of the incident beam, I over h nu. H nu is the photon, is the energy of photon in the beam. So this is the flux, that is F is equal to capital I over h nu. We can eliminate F from both of these equations and finally we get the following equation. That is I is equal to, that is the intensity of the incident beam, is equal to W into h nu over sigma. W is, you know, that is the stimulated or is the stimulated transition rate, that is the stimulated absorption rate and the stimulated emission rate for both, because both rates are equal. So I is equal to W into h nu. H nu is the energy of a photon in the beam and sigma is actually the cross section, which we clearly say that the absorption coefficient. So this is the absorption coefficient sigma over here. So you see that we can also write this W over here present in the numerator as 1 over tau St, where tau St is actually, St stands for the stimulated emission and 1 over tau is the transition rate of the stimulated emission. Not a stimulated emission but a stimulated process, because it involves two processes, stimulated absorption and stimulated emission. So 1 over tau St is actually the transition rate of the stimulated process, which we have replaced by the W has been replaced by 1 over tau St. The rest of the quantities are the same. So we have I is equal to h nu over sigma, which is the absorption coefficient, multiplied by the tau St. You can say that tau St is actually the lifetime of the stimulated process and 1 over tau St is actually the transition rate of the stimulated process. So this is the intensity of the saturating beam. So this beam will ultimately saturate the process. So we can say that this is the intensity of the saturating beam. The saturation intensity can be defined as, now we are going to give you the saturation intensity value. So looking just at this one, you look at the right hand side is equal to h nu over sigma into tau St. And you see that the saturation intensity will be equal to h nu over sigma into 2 times of tau Sp. Sp stands for spontaneous emission. So we have 2 times of tau Sp, because you know that under the saturation, when the saturation condition is reached, the two stimulated processes are compensated. That is, the stimulated absorption and the stimulated emission are compensated by each other. And only the process that will be responsible for the saturation of the intensity will be actually the spontaneous decay rate. So Is is equal to h nu over sigma into 2 times tau Sp. And we can simply write tau Sp, that is the spontaneous lifetime, simply by tau. So we have tau, we have Is saturation intensity on the left hand side is equal to h nu over sigma times 2 tau. Why this 2 tau is here? Why not only tau is present? Why 2 tau? To understand this one, we can go back to this equation. So you see that at saturation, the population of both level is NT by 2. So this N2 can be replaced by NT by 2 and N1 can also be replaced by NT by 2. So the two terms in the parenthesis will cancel out and we have 0 over here, and the last term, which is N2 over tau, replace this N2 by NT by 2. So you have in the numerator NT and in the denominator you have 2 tau over here. So So that's why we have 2 tau over here, because at the saturation the W will not be present. That is the absorption, stimulated absorption and stimulated emission will be cancelled out, and we are left only, that is the rate of decay of the population in level 2 will then be equal to NT, the total population, divided by the 2 tau. So 1 over 2 tau is actually then the spontaneous emission rate of the spontaneous process, or 2 tau, or where tau is the lifetime of the spontaneous process. So that's why we have 2 tau over there in the expression for the saturation intensity over here. IS depends on nu. You can see that IS depends on nu, and sigma. Sigma is actually the material parameter. Let's compute the ratio I over IS. We have I from here, and we have IS from equation number 7. So compute the ratio I over IS. You will get on the right hand side equal to 2W into tau. That is the ratio of the saturating intensity to the saturation beam, to the saturation intensity, is equal to 2W into tau. And we can write equation number 3 as, this is equation number 3, and we can replace, we can write equation number 3 in terms of the intensity of the incident beam and also in terms of the saturation intensity by replacing 2W tau over there. So replacing 2W tau in equation number 3, we can write delta N over NT is equal to 1 over 1 plus I over IS. So I is given by equation number 6 and IS is given by equation number 7. So let's compute the ratio of the power absorbed before saturation to the power absorbed at saturation. So you see that this delta dP over dV at saturation is actually the power absorbed at saturation, which is equal to NT over 2 tau into H nu. So we have one quantity available over here, and to that quantity what we have done is that we have multiplied by W in the numerator, as well as we have divided by W in the denominator, so that the right hand side would stay the same as shown in equation number 6, as shown in equation number 5. The other quantity that we are concerned with is dP over dV from equation number 4. So we are now going to evaluate the ratio of dP over dV, that is the power absorbed per unit volume, to the power absorbed at saturation. The ratio of these two quantities is dP over dV divided by dP over dV at saturation is equal to, so substituting these quantities, the common quantities will be cancelled out, and we are left with in the numerator we have 2W tau divided by 1 plus 2W tau in the denominator. And in terms of the ratio of the intensity to the saturation intensity, we have the expression on the right hand side of equation number 10 as dP over dV divided by the saturation value of the dP over dV is equal to I over IS divided by 1 plus I over IS. So we have answered all the questions of the questions asked in the question over here. So we have also expressed the powers in terms of the incident beam intensity and also the saturation intensity. We have also defined the saturation, and we have also defined the condition under which the population difference, that is N1 minus N2, can be kept constant or can be maintained. So this is the end of slide number 58.